You could run home. Okay, good. Okay, so I will talk first about Plancherel formula, and then I hope that I will have to run home and switch from analysis to algebraic geometry or getting Bill's camera, but now I have to agonize about this. So first of all, I have to write again the formula, and then I will try to give you some idea how the formula is proved. And I mean, I definitely cannot give you more than a very rough idea how the formula is proved. But today I'll try to give you some feeling what is important in the formula, how you should look at it. And then probably tomorrow I will talk about orbital integrals, and then you will see some techniques used in the proof. Today I will just vaguely refer to these results. So basically the formula looks like this, is the integral from 0 to infinity of the character of unitary principal series from the first sheet times m plus ni. This was this Plancherel density, which I wrote explicitly, plus, okay, one thing which I don't think I mentioned last time, but which is very important. You can ask why the integral from 0 to infinity. This is because, as you remember from the calculations, and also you can see by applying intertwining operators, that these representations for ni positive and negative are actually equivalent. So basically, you can integrate from minus infinity to infinity and put 1/2, but this is I mean, this is done in such a way that one irreducible representation appear only once in the formula. Then there is similar piece which comes from the other sheet of unitary principal series. And then there is the discrete part, which is the sum over discrete series. So these are integers different from 0, absolute value of n, theta n of f. So this is Harishchandra's Plancherel formula for SL2. And now I want to give you some rough idea why this is something one should expect, and why how one proves this. First of all, I mentioned last time that the proof uses Schwartz C space, Harishchandra's Schwartz space. So this is the space of smooth functions on the group with some rate of decay, which we discussed last time. Definitely, it contains smooth, compactly supported functions. It's a convolution algebra. I mean, it is in L2 of G. I mean, this is one thing I forgot to mention last time. It is convolution algebra. Another two technical properties which I didn't mention, that the right and left regular actions of G are differentiable. Therefore, of course, therefore I can differentiate this and I get the action of the Lie algebra and the action of the enveloping algebra from left and from right, and these were the actions I was using in defining the seminorms. And then what I indicated briefly at the end is that this convolution algebra is actually product of two close two-sided ideals. So, and one is the ideal of wave packets, and the other one is the ideal of so-called cusp forms. So this decomposition didn't appear in the first Harishchandra's proof of Plancherel theorem for SL2, which was just some kind of, there basically Harishchandra wrote this identity, and using various ad hoc tricks, he proved that. But except the statement, you learn very little from that particular argument. So in this argument using Schwartz space is the argument he used to prove the theorem in general, and this argument gives you some insight in harmonic analysis on semi-simple groups, and I want to give you some rough idea how this thing is done, because I think this is important to understand even on some very, very vague level, and this will motivate the results I will discuss probably tomorrow. Was the schedule fixed for tomorrow? Yes. Or Bill is working on it?
Okay, the score is 2-2. We did the schedule for tomorrow.
Okay.
We'll speak on the Plancherel formula in the afternoon.
Okay. Okay, so I will talk tomorrow about Harishchandra's invariant integrals, which is a tool which is used to prove a Plancherel formula, but it's also the tool which is used to reduce non-commutative harmonic analysis in a way to a commutative harmonic analysis. And today I will use this in a very heuristic fashion, because basically if I will try to combine both, I will get buried in technical statements and not get out of them before the end. So I will start with discussing cusp forms, because I mean, this is what was historically done first, and maybe it has some advantage because it is related to the things we, in some sense, understand. Cusp forms, there is a technical definition of cusp forms. I said last time, so this is the space C0 of G, is this ideal of cusp forms. There is a definition Harishchandra has, which is completely in terms of analysis on the group, that certain integrals has to vanish. But let me give you an equivalent definition, which is related to the Plancherel formula and related to the formulas for characters Peter was describing. Let me remind you that, remember that Peter stated this theorem of Harishchandra, which says that the character is given by locally L1 function. This function is constant on conjugacy classes, and it's given by simple formulas on so-called regular or regular semi-simple elements. And basically, in SL2, those elements are in SL2R are in two represented by elements in two cartons. So I will parameterize those. Okay, yeah, of course, we already have notation. The compact cartan subgroup is nothing else. If this terminology is not familiar to you, just do not worry about this. So we have K, which is cosine phi, sine phi, minus sine phi, cosine phi. This is a circle, and the regular elements here are all these guys except plus minus 1. So I don't want the so I take this minus plus minus 1. Excuse me? Yeah. And so this is our circle, and we throw out 2 points. And so therefore, our character will be given by a function on these 2 pieces. So it will be given by some analytic function. And you remember the expression is you have a linear combination of 2 exponential divided by the difference of 2 exponentials, which is fixed, so-called Weil denominator. And the other cartan is the cartan which is plus minus a. This is what Castleman was denoting by a. So this is e to the t, e to the minus t, 0, 0, t equals, t is in R. So this is so-called split cartan. And split cartan has 2 pieces, and each piece consists of 2 components of regular elements, because I have a piece which contains minus 1 and piece which contains 1, and we throw them away, and these elements, when t is different from 0, are regular elements. So our character formula in principle is given by some expression which is, again, a quotient of 2 exponentials, which Peter was describing on these 4 half lines. And so you got corrected versions of these character formulas. And I mean, when I was preparing this, I wanted to describe you Harishchandra philosophy, and then I look at Peter's table, and I saw that the philosophy contradicts the formulas. Fortunately, formulas had a typo. Otherwise, I would be in trouble. Okay, so what is important to remember about these formulas, and how these for characters? I mean, there are precise expressions there, and the only thing we actually care about in this business are 2 things. First of all, remember how you calculate the character. The character is given by a function which is constant on conjugacy classes. Therefore, you take your function, you integrate over a conjugacy class, and there is an invariant measure there, and I will talk about this more tomorrow because this is an example of so-called orbital integral. And then you multiply by the character, and of course there is some density coming from Weyl integration formula, and this gives you the contribution corresponding to that cartan, so either K and A. Then you do the same thing for the other cartans. So you have some picture like this for each cartan. You integrate over these conjugacy classes, and then there is this cartan which goes transversally. There is some density which comes from Jacobian in character formula, and then basically we have our character expression which Peter wrote. So the first important observation is that if you remember Peter's formulas, if you look at the sheet, then the characters of principal series live only on the conjugacy classes attached to elements which have real eigenvalues. So on the conjugacy class of elements which have eigenvalues on a circle in a complex plane, the character doesn't live. So an equivalent definition to Harishchandra's definition of cusp forms is that these functions here have the property that the integrals over conjugacy classes passing through these points in A all vanish. So therefore, on cusp forms, by definition, the characters of these principal series vanish. So on cusp forms, this part of Planchel formula gives us nothing. So for cusp forms, we should have the following formula. So now, if you look at this formula, then let's see, what did I mean, this is nonsense. I mean, there is no I. I was thinking about something from complex analysis. So remember that we call this number divided by 2 pi, so when we do this, is formal dimension. If you look at this formula, it looks formally like Planchel formula for compact groups. And Harishchandra's proof of this part of Planchel formula, it exactly mimics the proof in a compact case, with a lot of complications which show up in the proof, but definitely he was inspired by this. Okay, so now the first question is, I mean, there is this formal similarity. Does it go any further? So the first thing you can show quite easily is that matrix coefficients of discrete series are cusp forms. And using that definition, I mean, last time I faked and I used this as a definition because I was running out of time. Now I will explain to you using the definition is here that the characters, these are all functions as C of G on which these characters vanish. The orbital integral, I mean integrals, okay, this is the precise definition. I don't want to precisely define orbital integrals now because there are some normalization factors. But if I integrate a cusp form over a conjugacy class of any element in A plus minus, I'll get 0 as a result. So this is, you can take this as a working definition. I mean, Harishchandra's definition is formally equivalent to this, but it's basically, I can write the formula. He says that for any parabolic subgroup, the integral f of x n dn has to vanish. But, I mean, it's, then you don't see, to relate this to what I just said, you need a connection between this expression and the characters of principal series, and then you see that the character of principal series vanish on cusp forms. What I told you is the equivalent definition, which makes this more transparent. But, I mean, once we know this statement, then actually we can forget that definition of cusp form, and we will have much nicer description of this space. So why is this so? Again, I mean, the proof is more complicated, but let me give you a rough idea. First of all, it's easy to show that this follows basically from the asymptotics, or even from the formulas for leading exponents Peter discussed. You can easily show that matrix coefficients of discrete series are in Schwartz space. Because remember, if you apply, what do you have to do? You take a function, you apply left and right invariant differential operators. They're given by elements of the enveloping algebra. So what you get is another matrix coefficient. And then matrix coefficient has to have certain growth. And you have these asymptotic expansions of Harishchandra's. And you know for a discrete series that the leading exponent is a positive integer, and therefore when you are approaching 0, this decays rapidly. Yeah?
You're only talking about k-finite matrix coefficients.
Yes, by matrix coefficients I am only considering k-finite. I am not considering anything else because I'm always thinking about Harishchandra modules. And okay, when you raise this question in the proof, actually, Harishchandra's proof is a proof of formula which first proves it in the setting of the algebra, I mean Schwartz version of the algebra Peter mentioned. So Harishchandra first proves Plancherel formula for left and right k-finite Schwartz functions, which are dense in the Schwartz space. And then, because everything in the formula is a tempered distribution, is continuous linear form on the Schwartz space, then the formula extends in the full Schwartz space. So everything I will be doing will be on a k-finite level. Yeah, I mean, it's good that you pointed this out because I was just not... I mean, I'm just not paying attention to the other types of matrix coefficients, which we could do in this case because these are unitary representations, so they are genuine representations of the group, and we can discuss also other matrix coefficients, but their behavior at infinity could be much, much worse, and so we don't want to look at them. So, okay, so I have to tell you why these guys are here. I mean, okay, this is an argument which is kind of cheating, but if you write down the details, then it reduces to this fact. If you look at the eigenvalues of the Casimir on discrete series, and the eigenvalues of the Casimir of these guys, they are disjoint. So basically, if I, and the matrix coefficients of principal series are eigenfunctions of the Casimir. So you are integrating two functions which are eigenfunctions of a linear transformation, and this linear transformation is formally self-adjoint. This is what I think Peter was doing using in his calculations. It's easy to check. So they have to be orthogonal. So this means when I apply a matrix coefficient of one of these unitary representations to the Schwartz, to the matrix coefficient of discrete series, the result I get is 0. And then these characters as sum of matrix coefficients. So basically, when I apply the character to discrete series, to matrix coefficient of discrete series, I get 0. And this tells me that the characters of discrete series vanish on cusp forms. I mean, this is, yes?
You're assuming that the orbital measure is a linear combination of characters? Orbital measure can be, is some kind of, what is the relation between the orbital measure and the characters?
I mean, remember the formulas, what Peter had. You will have, you take the integral over the orbits and multiply by something, and you will have two exponential. So there is some Fourier transform argument involved. I mean, this is, I'm trying to give you just the flavor. I mean, there are technical tricks, maybe simpler, but I will have to write, spend 15 minutes writing various formulas which would drive you crazy. So don't take these arguments literally, but this is the idea. That you're right. I mean, there is, these are, you just Fourier transform thing in the right way, but you have a lot of these parameters, and for all of them this holds, and from this you can deduce this fact. Okay, so this kind of explains why matrix coefficients are here. Then you have to play various tricks. First of all, you have this space where the matrix coefficients lie. Remember, if I have two matrix coefficients, I can integrate them because they're in Schwartz space, and Schwartz space is in L2 of G. Then we can play the same tricks as with representations of compact groups. If I take two matrix coefficients of two different discrete series, the integral will be 0. Again, you can copy the argument we did in the case of compact groups, or you can argue, you should do this. Actually, if this integral is non-zero, then basically by linear algebra it will define an intertwining operator between corresponding Harish-Chandra modules, and because they are irreducible, they will have to be isomorphic. So I get that in cusp forms, I have this spaces of matrix coefficients for, so let me call dn corresponding discrete series, and they are MCDN is perpendicular to MCDM with respect to L2 inner product, exactly like in a compact case. If I take a matrix coefficient of one discrete series, then of course, if I integrate is absolute square, I will get something different from 0. What do I get in the case of compact groups? I get 1 divided by the dimension of the representation. Here, you prove also that you get a number which is independent of the choice of the vector. And that number you just define as 1 over the formal dimension of your, say, dn. So if you want, this is the definition of formal dimension. You see, I said that this 2 pi over n is called a formal dimension, but you can just, the definition comes from writing down the orthogonality relations. So orthogonality relations look like, say, pi x, say, v prime, pi x u prime bar d of x is equal to 1 over, say, d pi v u times v prime u prime bar, something like that. So these are orthogonality relations, and this number, and we don't know anything about it a priori, is called formal dimension. So then you get a very large subspace. Remember, each discrete series appears in the decomposition of regular representation infinitely many times, because you will have, if I fix v prime and I vary v's, I will get a subspace in L2 of G which is isomorphic to origin. So you really have a very large space of cusp forms which come from discrete series. And the point is, this is the equivalent, say, of Peter-Weyl theorem for compact groups, that the closure, cusp forms are closure of the space of all of these linear combinations of matrix coefficients of discrete series with respect to natural topology. And then the proof of this is essentially equivalent to the proof of discrete part of Plancherel theorem for the space of cusp forms. Because, you see, roughly speaking, this tells you that the value of any cusp form is seen by the characters of discrete series. The characters of discrete series are given as a sum of these matrix coefficients. So basically, you can easily deduce, easily, if you play with this, you can deduce the fact that if this formula holds, then basically these k-finite matrix coefficients have to be dense. And how the actual proof is done of this discrete part and of this density, you don't have to worry about these orbital integrals. So you look at the orbital integrals corresponding to the compact Cartan, to our k. Again, you integrate over conjugacy classes. You get some function on our k. Harishchandra shows that in the case of cusp form, what you get is a smooth function on a full circle. A priori, and I will probably discuss this this tomorrow, you could have jumps. I mean, you can show for arbitrary function in C space, this you could have something like this, that the function which is smooth on this connected components of the regular set, but when you approach 1 and minus 1 from different sides, the limits are different. But if you take a cusp form, then this is not the case, so you get the smooth function on the circle. Remember what Peter was saying. He had a formula for the character on a compact Cartan, which is basically I and phi divided by wild denominator, and there was some sign here which I don't remember, and it's not important. So basically, if you use this formula, you see that in the characters are given by Fourier coefficients, essentially, of these orbital integrals, which are smooth functions. And basically, the proof of this formula, through a bunch of tricks, reduces to Fourier series to the theory of Fourier series on the circle. I mean, this is very rough idea, and if I would want to give you details, it will take considerably more time. Maybe tomorrow, depending how much I will be able to say about invariant integrals, maybe I will give you some formulas which will make this equality clear. But basically, the very rough idea is that from the fact that orbital integrals on K are smooth for cusp forms using Fourier series on K, you can establish this formula. Okay, so of course, there was one thing I didn't mention, and Peter didn't mention, so let me spend just a few minutes explaining how one understands the characters of discrete series. Because, I mean, you can say how we use these explicit formulas, but we never describe how to get those formulas. So, yes. Yeah. Yeah.
On the other hand, in the compact case, the matrix coefficients, so you have class functions, which are sums of matrix coefficients.
Yeah.
So, but class functions, unless they vanish, shouldn't have vanishing integrals over conjugacy classes, right?
Yeah. No, but you see what I'm saying, that just the cusp forms had a property that orbital integrals, so you don't see cusp forms in unitary principal series. Orbital integrals of the conjugacy classes, of these conjugacy classes vanish. So the only things which do not vanish are related to the to the circle in the group. And so basically, you should think this as analogy of, say, Planchel formula for SU2, which has only a circle as maximal torus in itself. So in a way, non-compactness is lost and contained in this part which corresponds to wave packets. When you, okay, let me give you some additional information what is the how this analogy goes. So first of all, here another piece of analogy is that this is spanned, topologically spanned by, as in say as in Peter Wall, by matrix coefficients. You have orthogonality relations, like in this case. Also, if I look at discrete series, so I can look at my representation. So let's assume that pi n is a discrete I can look at pi n restricted to k. So this, you know that this is a sum of bunch of representations, say tau m. M goes over some set Sn. This is an infinite set of representations of k which appear in this restriction. These are just exponentials on a circle. And the theorem is, of course, you have here an infinite sum of exponential functions. The theorem is that outside of 1 and minus 1, this sum of exponential functions converges to a function in sense of distributions. And on the complement of these 2 points agrees to the restriction of the character of pi n in sense of Harishchandra. So this says that basically outside of minus 1 and plus 1, you can calculate the character of discrete series by just looking at the k-types appearing in the discrete series. Okay, now, I gave you enough information to do an interesting exercise. Look at Peter's calculation for finite dimensional representations. So here you will look at this discrete series. I think Peter described, and I think this is on the sheet too. No, infinite dimensional, the K spectrum. So from this, you can do formal calculation, and you can find the character of these discrete series representations and check if Peter actually copied the formulas correctly. So this is another part of the analogy. Now, of course, this explains the character of discrete series on conjugacy classes passing through K. The only issue, is what is the character of discrete series on the conjugacy classes here. And Peter wrote a formula, but there was a discussion why this formula is correct. There was a question, what are the numbers in this formula, and so on. So when you raise this question, let me give you the answer. You can show by just pure analysis what are the characters of discrete series. They are sums of matrix coefficients of these square integrable representations. You can, so these matrix coefficients are given by functions, which you know that they are decaying. So they will define definitely functions on Schwartz space. If you use these estimates and a little bit of analysis, you can show that the distribution you get on the group has to decay at infinity. If you have tempered, this is again a little bit of distribution theory. Tempered distributions are also called distributions of moderate growth. They grow slowly at, say, on Schwartz space on a real line, and there is similar analogy in the case of Harishchandra Schwartz space. So you can measure the growth of distributions in some sense at infinity. And you can show that the characters of discrete series have to decay because matrix coefficients decay, so the characters had to decay. This means then in Peter's formulas on A, there was remember, there are two coefficients and two exponentials, and only one of these exponentials can live, and this is the one. So for example, if I am looking in A in a piece when t is positive, so I will have minus nt times some constant here. So I have to have, as t goes to infinity, this exponential has to decay. So the thing you see from this, that any expression for discrete series characters on these four pieces will have only decaying term in the formula. So the only thing you don't know is this coefficient. And then Harishchandra has so-called matching conditions, which come from the proof of regularity theorem, which says the following, that if I essentially, the idea is if I look at the difference of the coefficients in the formula for eigendistribution on K, that this difference is equal to the difference of coefficients in the expression of the character formula on A. So on K, we can find this difference. We know what the coefficients are, 1 and 0. And then if you write a precise formula, here the difference is just one coefficient. So this tells you what this number is. So basically, the upshot of this discussion is that the character of discrete series is completely determined by the formula on K. The formula on A is uniquely determined by the formula on K. The formula on K can be calculated by restricting to K and doing the formal summation as Peter did using geometric series, as Peter did in the case of finite dimensional representations. So this is, essentially, this is how Harishchandra proved all the results about discrete series and their characters. So what Harishchandra did, Harishchandra actually proved that there exist representations with the character formulas Peter listed in general. In SL2, of course, one had a long time ago geometric models for these representations, but Harishchandra showed in general that there are formulas with this given characters, and those characters appear in a Planchel formula, and this said that this describes all discrete series and the corresponding part of the Planchel formula. So this is how Harishchandra classified discrete series and at the same time proved this, this part of, discrete part of Planchel formula. So this is a very, very rough sketch of the ideas involved in the, in the discrete part of Planchel formula. Any questions about this? Yeah.
Could you please repeat the matching condition?
The matching condition is that basically if you do it right, and I have I think here in my notes somewhere this, I mean definitely my notes on the web so you can find the right formulas, but essentially you have to be careful because there are these 6 components here, but basically you write the character on a compact thing, you look at the difference of the coefficients, and it has to be equal to the difference of the coefficients on the corresponding component of the split cartan.
What do you mean by difference of the coefficient?
Because in Peter's formulas, there were two exponentials. And this is the difference of these coefficients. Of course, I mean, there is something I'm cheating at. This is why I said you have to look at the notes, because, of course, there is a sign problem because I can take the difference one way or another. But, I mean, this definitely, if you know that this, do you remember, Henrik, how the sign is determined in matching conditions? Yes, yes, but yes, it's, so there is some, yes.
So my understanding is that without so a character is an eigendistribution.
Yeah,
This way we get exponentials in the form.
yeah,
But we also know that the character is given by a locally L1 function. That means we have like two open sets, one consisting of elements conjugated to A, and the other set consisting of elements conjugated to K, and they have a common boundary. On the boundary, the character has to be locally L1, and this is where the matching condition comes from, because you cannot have just arbitrary linear combination of exponentials and hold it to be locally integrable.
yeah.
You could always take a neighborhood which stays on one side of the common boundary. I mean, the local L1 should not impose any condition on the two different parts, because you can always take.
Yeah, I think it must be a bit more complicated. It's because, for example, you can take principal series which doesn't live on compact set, and you can take a principal series which, say, contains finite dimensional, or so there are, let's see, I mean, definitely there must be representations such that you take two discrete series. Yeah, you take two discrete series. This is the example. N and minus n. On the split conjugacy classes of a split cartans, the characters are the same, but they are different on compact cartan. So I think actually, of course, what you say is morally right, but I think you have to look at the behavior around the vertex of the cone. It's not that it's completely determined by these two. I mean, I will check it for tomorrow, but it's a delicate thing, because this is, I remember this was a remark Wilfried told me a long time ago when I was learning the subject, that you take theta n minus theta minus n. You subtract two discrete series, and you get an eigendistribution which lives only on compact conjugacy classes. So this is an example of an eigendistribution which kind of decays infinity as fast as you want. I mean, if you go to infinity on conjugacy classes, the distribution is 0, but its Fourier coefficients, which are, of course, matrix coefficients of this square integrable representations, have a finite decay. And this can happen for eigendistributions, but it cannot happen for characters. So there is some magic involved, but excuse me? No, I mean, in all these businesses between various components, there are several levels of complexity. There is eigendistributions and there is characters which impose even stronger condition on the behavior.
Maybe I'm wrong, but if I remember in a Iraqi's paper when the conditions were formulated, the reason for those conditions, actually for eigendistribution, comes from the following, that on each conjugacy class, when you just look at the formula, I'm sorry.
No, it's okay.
They define invariant eigendistribution on the regular set in order to make sure that the distribution also has an eigendistribution on the boundaries. You need to match this precisely corresponds.
Yeah, sure. No. This is definitely true, but I think what Matvei is saying, and I am a little bit worried about this, I have to look at the proof, is, if I interpret it correctly, that one, if you look at SL2, at the cone, nilpotent cone, that actually it comes from analysis of behavior here. And I'm not sure that that you don't have to also include the origin, but it's, I'll check it. Okay, so I have, 1 minute and 30 seconds, and I don't think I can, I can tell you what a wave packet is. So at least something, and then I'll continue tomorrow. So what is a wave packet? You take a matrix coefficient of this unitary principal series, because now I just have to understand this piece. I lied enough about this, so now I'll continue with this wave packets. And what Harishchandra does, he takes phi of ni to be a Schwartz function on a real line in a naive sense. So this is Laurent-Schwartz function. So function which is rapidly decreasing. I mean, Bill talked about this space so far on real line. And then you integrate from minus infinity to infinity phi of ni, phi. You see, for example, here in a formulation of Planchel theorem, I didn't want to repeat the integration, so my integral goes from 0 to infinity. I don't want to go from minus infinity to infinity. Here, I will do this from minus infinity to infinity so that I can use Schwartz functions. And I take n, m, so these are two k types, plus or minus I and e of x d n e. So what I'm doing, I'm taking a Schwartz function, integrating with matrix coefficients over the imaginary axis. And the statement is that such function, and I will have to make up some notation for it, but let it call it f of phi, this case, and just drop this n's and m's and plus minus. It depends, of course, on all these. Okay, I can minus, I'll devise some. So this function here is in Harishchandra-Schwartz space. You should think of this, and you will see much better analogy tomorrow. If you think about principal series, remember what Peter was saying, the leading exponents are 1/2, 1, and plus I and e and minus I and e. If you forget this, and this will be canceled out by something, then this is e to the I and e. So if I look at Lie algebra coordinates, I get that the leading term behaves like an oscillating exponential. So this is basically the leading term of this expansion you can view as ordinary Fourier transform. And this is the idea behind the wave packets, that we are going to take this wave packet, apply the character of the principal series on this wave packet, and then after a lot of struggle, you show that what you get back this function phi. So you have some kind of Fourier transform for wave packets, and when you write the corresponding Planchel formula, it gives you exactly these two terms. So this is how you get this other piece, but I will talk about this tomorrow. Yeah. Okay. I mean, this is just the matrix coefficient corresponding to, yes, you are, I was just dumb not to say it. This is the matrix coefficient of this principal series, the spherical function attached to k types n and m. Yeah. So. Yeah, I wanted to say something about this, but I didn't set up the notation, so I made nonsense out of this. So this isn't of the principal series. So I don't know, int plus minus I ni. Something like that.
So the wave packets are the things that look like they're integrated against these matrix coefficients?
Yes. Yes. But you see, the whole strategy is a combination of abelian and non-abelian Fourier analysis, and the Fourier analysis on the circle explains cusp forms. The Fourier analysis on the line explains this continuous part of the formula, and the continuous part of the formula is that you basically that these these pieces correspond to Schwartz functions on a real line, and then you integrate it with respect to matrix coefficients. And I mean, let me just finish, and then we are going to take half an hour break. When you raise this issue, remember that here this leading term in the expansion will come with certain coefficient. This coefficient was actually calculated in Bill's lectures. It is related, given by this formula involving intertwining operators given by gamma functions. So basically, we have something like Fourier series in the leading term times certain function. And this function is just such, as you will see, that it cancels out with the Planchel measure. This is how we get Planchel measure. So these coefficients in the expansion will give, as you will see, the Planchel measure here. And this is how the formulas for the Planchel measure are obtained. So this is, if you forget the rest of the expansion, this is just the ordinary, I mean, this is a very rough idea of the proof, just the ordinary Fourier transform. And because your the leading wave in the expansion of the matrix coefficient has a coefficient which depends on ni, you have to have here some function which is just the Planchel measure. So this is what will become clear, I hope, from the discussions tomorrow. Any other questions? Okay, so let's then have a, shall we have a half an hour break or? Oh, okay.